So the data again is just the production, industrial production in Spain. And we're going to convert it into time series. All we need is the second column and then specify which is the start date and the frequency. This has monthly data. So that's, I'll make it a time series. And it has 61 observations. So we have enough data to do to handle it and do forecasting. This is the plot of the data. So clearly we have a trend. Okay, so that means that we for sure will need to take a difference, at least one difference. Okay, the trend is very clear here, and we are going to check now if we have constant variance or if we need to make a transformation. So I'm going to do the Vox lambda with the Guerrero algorithm, and I get a lambda minus 0.07. So it's very close to 0. So I could work with the log of the lambda, with the log of the industrial production. One of the things that we observe here is that if you look at the plot, it has these peaks, okay, but it doesn't look like the variance is changing. So we'll do it with the log, but we'll start analyzing first the original series, because it doesn't look very much like the variance is changing. If you look at the variance here, except ignoring the peaks, okay, you can imagine a few lines here. Let me just draw them, annotate. I'm going to draw a few lines. Except for the peak, you can look at the spread here, and the spread looks like this. Okay, I put a little bit wider than it is. Here, this peak here is making it look like an increasing variance, because the spread here, we could view it as this spread, which is that larger. But then again, we have roughly the same spread as in the original, as in the first piece of the time series, and also here we have roughly the same spread. So it's not that clear that we need a transformation. And so I'm going to start working with the first original series. Okay, and put a cross here. And I'm looking at the autocorrelation function of production, and the autocorrelation with the ACF2, we get the ACF, the autocorrelation function, and also the partial autocorrelation function. The ACF shows it's dying slowly, and we have a significant spike here. That's a year after, that's 12 months apart. So we'll look at this first difference first. So I'm going to take the first difference, okay, of the prop, and look at the ACF and the PACF. And now the ACF and the PACF are showing that a pattern of stationality, right? If you look at this thing, you see that this is month 12, this is month 24, and month 36, and so on. So it looks like something is happening every 12 months. So when we see that behavior in an ACF or in a PACF, that immediately points at some seasonal behavior. So it looks like we have some seasonality of order 2. Okay, the seasonality could be of order 2. Now, if we look at the non-seasonal part, if we look at the first few lags, we observe that in the ACF, the first autocorrelation is significant. Okay, and here we observe that the first 3 autocorrelations, partial autocorrelations, are significant. Okay. Now, this is dying slowly. Okay, this is dying slowly. The seasonal component the ACF of the seasonal component is dying slowly. So we may try to take a seasonal difference to see if that helps, or if we are already over differencing. So I'm going to take here the 12 difference first and see how it looks. I'm going to say take the 12 difference, the difference of order 12 of the first difference, because definitely we need the first difference to remove the trend. So we now take the 12 difference. This will be the seasonal difference, and that's the 12. I'm calling that D12, D1 to remember that results from taking the seasonal difference of order 12 of the first difference. Now I'm going to look at the ACF and PACF. And now what I observe is that the ACF, only the lag 12 is different from 0, and the rest are 0. So now I can say it's dying it's dying fast, because only the first ACF is different from 0. And looking at the non-seasonal, at the PACF, and looking at the non-seasonal part, we observe that there are 2 partial autocorrelations that are significant, and there's only 1 here. And we observe that a decay here that looks like a sine wave, okay? We observe this type of sine wave decay. So one of the models that we could try is 2 autoregressive terms on the non-seasonal part. And if you look at this one, we could also have 1 autoregressive term on the seasonal part, okay? Because you only have 1 significant lag at lag 12. We don't have more than that, okay? The rest are 0 at lag 24 and lag 36. I could extend that. Instead of doing it 24, I could do it 36, so that I can see later in time how it looks, okay? And we observe that the only significant lag here is the PACF at lag 12. So that could be an AR2 on the non-seasonal part, and an AR1 on the seasonal part, okay? Now we need to check if we over-differenced. So to do that, we compute the standard deviation. I created this function so that I can do the computation for the standard deviation for the 3 series, the original, the first difference, and the 12, and the seasonal difference of the first difference in the same command. And I need to do that. We have seen this because if I just apply the function directly, if instead of putting here std_def, I will use the function sd, then it will give me NAs for the first difference and second difference, because I need to specify that it needs to remove the missing values. Okay, so that's why I built this function. Then I just say apply. Apply, remember, apply is going to apply the function that I specify here to in this case, the columns, because margin is 2, it's the columns of the data frame formed by the production, industrial production, the first difference of industrial production, and the 12 difference applied to the first difference of industrial production. Okay, apply that, and I can see the standard deviations. And as you can see, what the standard deviation for the 12th difference of the first difference, that is the 12th seasonal difference of the first difference, is smaller than just for the first difference. So I'm not over differencing. Okay, this confirms that I am not over differencing. Okay, so we confirm we need 1 seasonal difference and 1 non-seasonal difference. And from what we just discussed a few minutes ago, it looks like I should fit 2 autoregressive terms on the non-seasonal. Remember, this is always, remember that when you run Tsarima, it's always the time series, and then P, D, Q, then P, D, Q, and E. Okay, that's always the sequence, the order. We specify first the non-seasonal parameters, the order of the non-seasonal part, and the order of the seasonal part later with the seasonality. And we have seasonality of 12, so we have two autoregressive terms on the non-seasonal. One autoregressive term in the seasonal part. We'll have one non-seasonal difference and one seasonal difference of seasonality 12. Okay, that looked like the right model, as like it could be the right model. So I run it, and if you look at the diagnostics, I mean, we see this big jump here, okay, and that's because of that there's one spike that's longer than the others in the original time series. That's probably the cause of that. The normal plot looks reasonable. I mean, it's not ideal. Ideally, everything will lie on the straight line, but we have some outliers, so that's to be expected. And the p-values of the ACF of the residuals looks very well. It's all noise. That's what we expected. And the Young box statistic is the p-values are very reasonable. Right? All of them are greater than 0.05. Okay, so it looks like it's a good model. It looks like it's a good model. So I'm gonna take I'm gonna check the coefficients, and all the coefficients are statistically significant. Okay, so it looks like then we have a good model. Okay, now let's forecast 10 periods. Let's forecast 10 periods. And to forecast a SARIMA model, we're going to use the function sarima.for or forecast, and we specify the data series, the time series, how many periods ahead we want to forecast, and the order of the SARIMA model. Okay, we specify those, and then plot dot all equal true, so that we get all the plots and the series with the confidence intervals and so on. Thing, and it gives me here the plot of the series, and this is my forecast. These are my forecasts. Okay, the red line are the forecasts, and then the first these intervals, the gray, the darker gray, let's say, region is showing the 80% confidence intervals, and the other ones, the lighter gray, is showing the 95% confidence intervals for those forecasts. Okay, so the forecast is following the pattern of the series. So in that sense, it looks a reasonable forecast. Okay. Now, remember that we said that to evaluate the performance of a time series model, it's always convenient to feed the model with the first part of the data, and then leave some observations at the end that we already know the values, forecast them, and then compute the root mean square error of prediction. The prediction means mean root square error. So we're gonna split my data into a training set, and for that I'm gonna take a window of the original series that ends on the January 1982, and so I have all the data up to January of 1982 in the train series. So prog train then would have 50 observations. Okay, it has 50 observations, and I'm going to forecast the rest of the data. So I'm going to create my test set as starting in 1982, the second month of 1982. Okay, that'll be my test set. I know what the values are for the series in that period, so I can compute the prediction error. Now I fit the same model. Hopefully that will fit well to the train data. And so I'm going to say mod tool.train. to specify that that model is estimated only with the training data. And I say it's ARIMA, it's the same model. I'm trying here. The coefficients are all significant and the diagnostics look good. Okay. If they did not look good, I mean, suppose that they didn't look good, that meant that the model that I was using is not good for the whole series. Okay, and I had to go back to the identification stage and try to fit a different model. Now we forecast the series, and we're going to forecast. I left 12 observations outside, right? On the test, I have one from 11. I thought it's 11 only observations, but anyway, for the test, I have 11 observations. So I'm gonna change this thing. I know that's right. Ahead is 11 observations. So I'm gonna forecast using the arima.for function. Broad train. Now the model is the one that I built with the training data set only. 11 periods ahead, because that's the size of my test set. The model that I already specified to feed it, and then plot all equal to, so I can see the whole thing, all the plots. There's the plot. These are the forecasts. Okay, these are the forecasts. Now I want to plot the original values also in same chart to see how the forecast will be represent the actual data. So to plot the whole thing, I just add a lines function to add the lines for the production data. And now I have the actual forecast, actual forecast, sorry, this black, and forecast. So I have all the actual data points and their forecast. So they seem to give a good forecast. I mean, this model seems to be giving good forecast for the data that I left behind for testing. Okay.
Teacher,
yeah,
I have one question there. The black line of the estimate are real dates, are real data.
Yeah,
are not simulated, right?
That's right. Yeah.
Okay.
These are the red. This says the black is the actual data, and the red are the forecasts.
Okay, so it got very close, right?
Yeah, it's very close. Okay. Looks very good. Looks like a very good forecast. I mean, the only one that seems far away is this one here, where we have the actual is here, and the forecast is down here. That's the only one that looks very far away, but the rest are reasonably close. Okay.
Thanks, teacher.
Now that's just a visual check, but we need to check now what's the root mean square error for prediction. Okay. Now, if we want to plot the actual values and the estimated values in the same plot, we can use XCS to join the series. Okay. So, for example, this one is this is what we already computed here. Is the same thing, forecast plot test. So I'm not going to recompute this thing. Is the forecast for train 11 periods ahead and so on. And now I want to plot the estimated values with the model together with the actual values. Okay. So what I'm going to do then is I'm going to take first I'm going to compute the fitted values. That is the values that I estimated with the model for all the series, all the fitted values. How do I get the fitted values? I get the residuals. I get the residuals and subtract them from the actual data. Okay, remember the the residuals are the observed minus fitted. So I subtract the fitted values from the observed, and I get the fitted values for the series. This we normally don't do, but it's not necessary to do it. I mean, what matters is what's happening here with my forecast. But let's suppose you want to fit the estimated series with the model and the forecasted and the actual series. So now to convert to a structure, we can do that joining the series, and to do that we convert them to another time series object, which is called XTS, which has other properties different from the TS object. So we use the TS Studio package, which we already installed, to do that. And the way we do it is we say we convert XTS to TS. The fit forecast is XTS to TS of the fit forecast, and converting that. And then I just put the lines in red for the estimated, and in black is for the actual data. So I can see now this is the estimated line. This is the estimated series with the red ones, the red lines, and this is the actual data, the black lines. Again, this is not strictly necessary to do. What matters is more to take the series, plot the series, and then look ahead and see how the forecasts are performing. Now let's calculate the root mean square error, the prediction root mean square error. To do that, there's a function that's very useful. It's called the RMSE function in a package called model matrix. That's a very practical function because we don't need to, we could do it by hand, computing the differences and then squaring them and then taking the average. But this function does that for us. What we are going to do is then from the library model metrics, we use the function RMSE, root mean square error, of what? The difference between the forecasted values for the testing period with the actual values in the testing periods. So this function works with two vectors. One vector that has the estimated values and the other one that has the actual values. And then we can compute the root mean square error. So these are the forecasted values for the test period, and these are the actual values for the test period. And that gives me 7.24. Okay, that's in the units of the series, of the time series. Now it's very useful to do the same thing, but as a percentage of the percentage of the actual values. In test period. Okay, so I'm gonna take here as protest thread. So we're gonna see the root mean square error as a percentage of the actual of the what we obtain as root mean square error divided by the mean of the observations, the actual data in the period that we forecasted. So I'm calling this our forecast RMSE. Forecast RMSE is this root mean square error, and divided by the mean of the test data in the prediction period to see how far in percentage I am from the average. This is hard to vectors. Protest. It's protest only. See, here we use the dollar sign because forecast.prot.test has a structure. Let me show you here. So if I say structure of forecast growth test, it tells me that it has two components, the predicted values and the standard errors. So that's why I want to select the predicted values, and that's why I use the function as vector, so that it converts that to a vector, and I can compare it and compute the root mean square error. Okay. So I compute this thing, and it tells me that the root mean square error is about 4% of the actual mean, the mean of the actual values in the test period. So on that test period, my root mean square error for prediction represents roughly 4% of the mean value, which is a reasonable precision for forecast. Okay. Now I'm going to compare now this thing with the with exponential smoothing. The automated, remember that when we talked about exponential smoothing, we saw a function to do that thing automatically and automatically choose if it's if the seasonality is multiplicative or additive and so on. So for that, we use the function forecast, and I'm going to call that model fit_auto. That's my model. If I look at the summary, I have my forecast, my 80% confidence interval, and my 95% confidence interval. Now I'm going to plot it. And I have a plot that looks similar to what we saw earlier. But now this is the exponential smoothing forecast. Okay, which is also very close. Now I can compute also the root mean square error for these forecasts. Okay, so I'm going to say fit auto train. I'm calling that to the forecast of production train, the part that has only the training data, and then I compute the RMSE the same way as we did before. I'm going to put an enter here so you can see we use the function accuracy for and I'm going to compute the accuracy of forecast from the fit auto train, from the model that I fitted with exponential smoothing with the automatic fitting function that it has, and the difference with the production test. But I do that thing only for the columns test set and RMSE. To understand why I do this thing, let me look first at, I'm going to do an intermediate step here. I'm going to cut this thing up to this point. Control V, and I'm going to put it here. I'm going to add it here. I'm going to say accuracy equal, and I'm going to copy that thing. Control V. We didn't copy it. Let me show what's happening. My right button in the mouse is not working. Copy. Okay, finally. And then I'm going to say here paste. Okay. If you look at the structure of accuracy, it's okay. Let's see. What did I do wrong? I need to, because I'm selecting the test set and the RMSE. Let me repeat this thing. And I'm going to say FSST equal, I'm going to copy only this thing. So, see, I'm doing something wrong because I need, what I really want to show is that ACC, structure of ACC, it has to give me the components, because ACC is a list. When I compute this thing, I get a list, and the list has several components. One of them is the test set, and the other one is the indicator. I'm going to compute the RMSE for the test set. That's why I indicate this thing here. Forecast video train. No. Let me remove this thing for a while. No, but only remove it, cut. Okay, here it is. See, this is a list that I have here that has several components. I have a vector of numbers, okay, and has two dimensions. So the two dimensions are training set. I have a set for training set, and I have another one for test set. All I'm interested in is in the RMC computed with the test set, okay? And the only statistic that I'm interested in, I could choose several statistics, but I'm with the accuracy function, I could use several statistics. I could use, this is the mean absolute error, this is mean square error, this is root mean square error, mean absolute value, mean absolute error, and mean predicted error. Okay? But I want that only for I want this one because I want to compare with what I already computed for the other model. So I want the RMSE, but only for the test set. That's why I specify here that I want this thing, but only for the test set, and I want the RMSE, the root mean square error. Now, when I do this thing, now if I do the structure, it tells me just a number. It's 9.56. Okay, so the mean square error is greater than for the SARIMA model. Is 2 units greater, 2.7. The other one was 7 point something. And this is 9.56. And as a percentage, I do the same thing. I compute the percentage, what this root mean square error represents in percentage of the mean of the test set, and that's 5.6%. Okay, and the other one was about 4%. So in that sense, I would retain the forecast. I would retain the model, the SARIMA model, because it gives me a smaller root mean square error for prediction. Okay. You can now do. I'm going to split you in groups, and you're going to do this same analysis. Remember, lambda turned out to be close to 0. So do the analysis now with the log of the data. Okay, do the analysis with the log of the data. Now, when you compare it with the exponential smoothing, so that you can the comparison is fair, you need either, although in exponential smoothing you don't need to make the transformation because you don't need to stabilize variance in exponential smoothing. To be able to be fair in the comparison, you will need to fit the exponential smoothing model to the log of the data. So do the same analysis, but with the log of the data to see if that lambda helped, and we can get a simpler model or more accuracy in the forecast. That's why looking at them as the average, as a percentage of the mean of the true values is useful, because it doesn't work if we're working the original units or if we're working on the log units. Okay. So you're going to do that with the log of this thing, and you are also going to work on the series. You're going to work also on this series that we already analyzed, the electric production data. that you already have in Brightspace, and you already analyzed it here. Remember that for electric production data, we finally got a model that looked reasonable. It was difficult to get to a model that was reasonable. We finally got it. We got to a model that was reasonable with the p-values for the Box-Young statistic. Only the first p-value was very close to 0.05, and the rest were above 0.05. So do that analysis. Also, the forecasting forecast. You choose it to forecast, let's say, 10 periods ahead. Okay, in this electric production data, let me remember how many data points we have here. That's EPROV. We have with 397 observations, and we have monthly data also here. Okay, we have monthly data. So forecast with this one, electric production forecast 12 periods ahead. That is 1 year. Okay, forecast 12 periods ahead in the electric production data. After you do the analysis and forecast what we just did, but instead of working with the industrial production, work with the low of the industrial production. Okay, is that clear what you have to do?
Yes.
Okay, so let me pause.